So we walked in to the meeting and they start talking through and I'm like, what do you want out of a human habitat? And literally this guy said, no humans. We're like, oh no, this is terrible, right? When we came into this, we had a large number of potential customers in mind. And one of them was, 3D printing of organs. We said, hey, a billionaire is going to pay a huge amount for an extra pair of lungs. And, we'd read these articles online saying, hey, this is going to be the next big thing. So you don't need to have a $23 million toilet, for instance, like you do on the ISS, because you've got, the simulated gravity environment. And so it reduces the level of technical expertise needed for fixing a lot of, the regular problems that you might get, when living in an apartment in space, if you will.
Welcome to Space Terminal, the show where we sit down with founders defining the next century of space infrastructure. Our listeners are leaders, operators, officers, and partners building frontier technologies. Lee, welcome to the show. I'm going to turn back a couple chapters and start from Caltech. From there, you went to Momentus and now Astracene. Space innovation is a prominent motif across your career. What sparked this passion?
The longer answer is really that I enjoyed it because it showed what's possible, what this sort of exciting future could be for all of us, a thing to look forward to. And I really sort of got my chance when I was about sort of 16 or 17 back in New Zealand, growing up in a small town, middle of nowhere. But I got the chance to go to the International Space School in Houston, in Texas, for about 2 weeks. And there we learned all kinds of exciting things. They cut open an astronaut's glove, showed us, the sort of possible world, and laid out a path forward to working in the space industry, which was do, an undergrad in mechanical engineering in your home country, and then a master's or PhD in the US. And that way you could get into the space industry, move forward, and really actually become a, set of exciting possibilities for me. And so I followed that course for the next, 10 years. And, it makes it sound like it was a single process just getting there. But it was really many steps along the way.
NSF, or the United States National Science Foundation, awards you $275,000 for artificial gravity space habitats. What made advanced manufacturing the right wedge?
The reason why we approached, artificial gravity simulation at the beginning, which is effectively using a centrifuge in space for simulating gravity, was that lack of gravity is terrible on the human body. But on the flip side, you really need microgravity for all the processes you want to do in space. And so we came up with a design where we could have this inflatable habitat and then a centrifuge on the inside. And the reason why, in-space manufacturing is the way that we've really sort of focused the company now is because that is where there's this huge potential. For humans in space to make sense, they need to add more value than it takes to keep them up there. And so there's really a limit in the amount of science funding you can get or government funding. And so you need to find something else. And in-space manufacturing provides an opportunity because the markets on Earth in the hundreds of billions of dollars. And as that industry develops, there will be room for people to be performing R&D in space around manufacturing processes, which will finally, separate that out from purely government funding and mean that with this decoupling, the industry can just keep growing instead of having the cap that it currently does now.
You posit expandable, non-rotating space habitats are the solution. Can you walk me through your decision tree and why were other approaches sequestered?
Sure. There's really a couple of aspects to this. And the first one really comes down to when we started this project, we knew that there were health effects around the effect of microgravity on the human body, whether it's bone loss, whether it's, the lack of tasting properly, whether it's vision impairment. It's really not great for your health, especially long term. And so we were saying, okay, we need to add this artificial gravity portion in. But there's a couple of challenges, which is that the whole reason you go to space is for the microgravity environment, whether it's for the research, whether it's for the manufacturing process that you just cannot do on Earth, even just looking out the window. You don't want to be in a rotating space station looking out the window. It's not fun. And so I think where we really got our approach for that was realizing two things. One, that the common knowledge that everyone has around the radii you can accept in a centrifuge for generating artificial gravity and people living and working in it is much smaller than you realize. And there's a couple of nuances to that I can go into. And then the second thing is that you still need a decent radius, but we could put that inside an inflatable habitat. And so what this does is it means you don't have rotating seals. You have the ability to live and work in a artificial gravity environment and then move out to the microgravity environment for all of the other applications that you need to do, and really sort of pairing this together. And that was sort of the thought process that led us in that direction. Really, realization about the radii for a centrifuge that's needed is what inspired the whole approach.
Space habitats access both microgravity for research and artificial gravity for humans. How do you maintain structural integrity? How does it not just tear apart?
So that's a fantastic question. And whenever you have a rotating system in space, if you have something moving around inside it, for instance, a human or a piece of equipment, or even just fluids, that can change the center of mass. And if that center of mass is not aligned with the axis of rotation, the entire system can wobble. And so that's particularly important for us where we have a non-rotating section and a rotating section together. But even for just a fully rotating platform, such as what VAST was proposing, if that center of gravity moves, then you're wobbling the entire station. And anything that requires, low vibration doesn't work. Even docking becomes tricky if your whole station is moving. And so what the NSF grant was around was focused on the ways of stabilizing the system. So actively maintaining the center of gravity to be through that axis of rotation and doing it very quickly and efficiently.
Is radiation a material risk for space habitats?
Yes, there's a couple of aspects to that. So radiation can affect your electronics, for instance, causing bit flips. So you really have to be sort of software specific in terms of the ability to cope with that, or you use, traditional radiation hardened electronics. Now, the radiation can also be a challenge for, the habitat shell itself, depending upon what polymers you use. So you have to be really careful that because we're using inflatables, that this does not get eaten away at by UV radiation and so on. But that's not, there's solutions to that. I guess, the important one is also for human habitats is making sure the humans don't experience excessive layers of radiation. And the approach to that is typically to just add more mass into the system to really protect it. And so as the cost of launching material into space goes down, the ability to add more mass actually goes up, which is good. There's a couple of other clever ways of doing, electromagnetic protection for people, but that requires a lot of power. But with the advent of space-based solar power and other very large solar platforms in space, that may be an option too.
Just a quick clarification for our audience. How would you add mass to counter the effects of radiation for humans?
Sure. So there's sort of two approaches, really. So one of it is that you pack everything into a single launch vehicle, and then up it goes and then expands outwards. And in that case, you're really limited to the total amount of mass that launch vehicle can have. Now, the second approach, which is the one that we were taking, is to provide areas within the platform that you could add additional mass afterwards. Water is a great example that's typically used because you need to have it anyway. And so in that case, you really have these pockets and you add mass there. Now, the final way is really to use equipment. So you have, for instance, on the ISS, you've got these equipment lockers and racks, on the outside, or rather on the inside, but against the walls, and these can just provide additional ones blocking. Now, what's interesting is the type of mass you add is important. Water is great because it really blocks it, but, thin metals, you can actually get what's called secondary radiation, where a particle hits it, and then, it becomes more of a shotgun approach of, secondary radiation. So you do have to be careful about the approach you take, but there are ways and means of doing so. And so that also depends upon what orbit you're in. The lower your orbit, the more drag you get. It just gets thinner and thinner and thinner. And the second aspect in terms of the amount of mass you can launch that's relevant to us is if you have a rotating centrifuge, then the centrifuge system itself needs to be designed to accommodate however much extra mass you have. If all the people on your platform congregate in one area in a rotating section, that changes how much mass you need to compensate for versus if everyone's spread out the entire time.
Can you speak more to the structure of these habitats? How amenable are they as payloads? Do they need a specific launch flight, or are they plug and play into any launch vehicle?
Yeah, that's a great question. So in terms of modularity versus non-modular, in some ways you want to have the largest system you can that can be launched in one go, and that being your sort of modular piece. What is nice is the ability to test a system entirely on the ground. And so that's where having a larger module, if you will, comes in handy, because then you need fewer modules. Now, modularity really shines when either you want to produce the same one multiple times, in which case the cost actually comes down quite significantly, or when you just need to keep on building your structure in space, beyond what you can initially do. When it comes to sort of launch vehicle, the way, the large habitat for humans that we've been designing is focused on really requires something sort of a starship sized. And the nice thing with inflatables is you can make it larger than the fairing, but there is a limit to how much you can package in. And so the ability to package this very large expandable habitat with an internal centrifuge that unfolds requires something of the starship scale for the larger ones that we're talking about. Now, we do have variants where everything's scaled down, fewer people, smaller, which can go in the smaller launch vehicle. But of course, kilogram for kilogram, that becomes more expensive. So there's really sort of a set of trade-offs here.
You mentioned that in terms of commercialization, there is a human aspect and then there's a research aspect. So how does your testing differ when you're testing for both systems?
Sure. So the way our company is structured is we're first starting with, unmanned platforms, and then that allows us to validate a lot of technologies as well as serve markets that don't necessarily need humans. And then the follow-on step from that are these human habitats. And so in terms of testing, this approach allows us to test in space these technologies at a much smaller scale. This gives us more confidence while also ensuring that we don't need to be 99.999% sure that the system will work from the get-go, because we can iterate more quickly with the smaller units while avoiding any problems around human health and safety, and yet still generating revenue for us by having these platforms serve, research markets, manufacturing markets where humans in the loop may not necessarily be critical or even desired in some cases.
Could you walk us through your products? And what is the biggest technical constraint to scale from unmanned to manned systems?
Sure. So on the unmanned system side, we've really sort of got two key platforms. One of them is, purely a robotic platform, really designed, robotic arms, for instance, designed for hosting processes that don't require atmosphere and maybe not even need humans in the loop. And this is one thing we discovered because we started on the human habitat side, and we discovered that there are groups that don't necessarily need or want humans in the loop for their particular subsystem. And this can be because they use toxic materials, or very high temperatures, or even just having, vibrations being present from people disrupting the particular processes. And so crystal growth is a good example of this. You don't necessarily need an atmosphere for it, and having this perfectly still environment is very beneficial to the crystal growth. It's almost why you go to microgravity in the first place, so you avoid the disruptions you get from being on Earth. So these are comparatively small platforms, but we can build multiple ones of them, and they're really designed to operate in low Earth orbit. This leads to the follow-on one where we actually have the same platform, but with an inflatable section, and this really allows us to move more into the biology market. And then the follow-on one from that is actually the human habitat, where we still use that inflatable technology as well as the artificial gravity, centrifuge on the inside to really provide the best of both worlds in terms of human health and yet the access to microgravity.
And these are designed for LEO currently, but in the future, as we scale to Geosis, Lunar, how easy is it to scale that technology? Could you walk me through the design?
Sure. So in some ways, these habitats are even more critical to further away from Earth because you're spending longer in microgravity, which becomes worse for your body. Now, the key difference you get is the radiation environment. When you're closer to Earth, you're protected by the Earth's, magnetic shield. Further away, you have to experience the full environment of all the radiation. And then if you're going to say, making a habitat on the moon, for instance, you have additional challenges in terms of both temperature extremes, because you may be in darkness for 2 weeks versus in the light, or the actual dust environment on the moon is very harsh. It's almost like, very small glass shards, or like volcanic ash in a way, that can really just eat through seals and eat through systems. And so, for the use of these ones, one, of course, you need additional radiation shielding, but, that's a solvable problem, shall we say, as I mentioned. In terms of, for instance, on the lunar surface, you have to be just careful about how the dust is handled. Dust is fine if it's just sitting there. It's more if you've got rubbing, that's where the problem occurs. And we do actually have a patent pending around how to make inflatable structures more resistant to leaks and more safe even if a leak develops, because that's really important for these systems. And that's even more important when you have an environment where you have these very small shards of regolith that could be causing problems.
And the ISS crew infamously spends half their time on repairs. When something breaks on Earthshine, hopefully not, who fixes it?
Yeah. So with the human habitat, humans are the ones who will be doing the job. One interesting aspect is that because we've got an artificial gravity section within this habitat, we can actually use designs that are used on Earth, whether it's, the life support system, for instance, as an example, or in the heating system, and a variety of them. So this really allows us to have more replacement parts, and it means that the parts that we do have are not bespoke in the same way. So you don't need to have a $23 million toilet, for instance, like you do on the ISS, because you've got, the simulated gravity environment. And so it reduces the level of technical expertise needed for fixing a lot of, the regular problems that you might get, when living in an apartment in space, if you will. When it comes to the outer shell, there are options that we're looking at for both human repair or robotic, but the actual patent that we're applied for around the leak-resistant shell actually allows for a lot more options when it comes to repair and maintenance than the current approaches.
What are some lessons we've learned from ISS, and how are you applying that to extreme heat, cooling, not just in LEO, but eventually for other orbits as well?
Sure. So one of them is that you don't have natural convection. So on Earth, gravity causes, hot things to rise, for instance, and cold air to fall. We don't have that in the same way on the ISS. And so that means that you can get these pockets of warm air or cold air, as an example, within the habitat. And you constantly have to be moving air around with fans, not just for the temperature, but also to move CO2 around and force that through filters. Now, the great thing about having an inflatable habitat with a large centrifuge in it is you can actually use the motion of that centrifuge to create these air currents, which means you can move air around the system, evening out the temperature that the astronauts experience, so that even though one side may be hotter and one side colder, you can mix that far more easily. Got this huge fan, if you will. And it also allows for the air conditioning, if you will, throughout the platform. The other aspect is really on the shielding side. The more layers you have, multi-layer insulation is the name, the more you can reduce the extremes that you see. So while the outermost layer sees these extremes, the innermost layer remains this nice, even temperature. And so that really applies on the human side. On the non-human one, for instance, we make sure that the components are more resistant to that. And by not having humans in the loop for those autonomous systems, it's a bit less of a problem.
Beyond the multi-million-dollar toilets and the air conditioning systems, what is the biggest cost item? What's the cost structure like of setting up these space habitats?
The mere fact of the total cost for this is in some ways why we are starting with these uncrewed platforms, because that actually lets us go out and validate these technologies far more quickly while still generating revenue. And what's exciting is that also allows us to help incubate the in-space manufacturing industry by hosting the equipment needed for those processes on these platforms. So then the follow-on one makes economic sense because these markets already exist. So in terms of what the cost structure looks like, we would rent time on the platforms for astronauts, whether it's government astronauts, whether it's space tourists is a good example. What the biggest cost is, there's really a couple of pieces. So one is, just the launch of the full system itself. The second one is actually the transportation costs of getting people to and from, because from the customer's perspective, they just see the entire cost, not just what goes to the habitat platform itself. And then honestly, the third one is just the sort of R&D required for ensuring that human health and safety is respected as much as it needs to be, so that everyone's safe and secure and happy. And that's actually one area where the approach we're taking has some advantages because of the fact that we can use these terrestrial systems and we don't have to do the R&D on absolutely everything. It is still expensive.
How are you monetizing the systems? Does it differ based on manned or unmanned?
Absolutely. So unmanned is orders of magnitude less expensive than manned platforms. And so the way we monetize the unmanned platforms is effectively you say, hey, here's this, robotic platform that lives in low Earth orbit, and we can get payloads delivered to it, and then work with partners to have those payloads returned to Earth if they need it. And so we would charge both on the total mass that goes up, since that's in some ways how our partners charge things. And then we say, hey, we're providing this much power, thermal control, communications, and so forth, and the duration, right? Some customers say, hey, our process takes a couple of weeks. We only need to be there for a couple of weeks. So I said, great. We can replace you as soon as you come up, and you've done your mission. This is particularly true of manufacturing because they just want to process everything through as quickly as they possibly can. They don't need to sit up there for several months. They don't want to sit up there for several months. Human side, right, as I think I explained in terms of, just renting the system out to agencies as well as individual customers. But, that would be more of a case-by-case basis in terms of the duration and what exactly they would need from the platform.
Can you take me into customer discovery? Who are your customers?
Sure. So there's several different customer groups, and it also depends upon if we're talking about the uncrewed system or the crewed platform. So there are the groups who, you need to use the platform. So you've got, let's give it a good example. So there's the companies who want to do manufacturing in space. So what do I mean when I say manufacturing? I mean that, for instance, on the semiconductor fiber optic side, you take a product that you've made on Earth in some ways, you send it up into space, and then you recrystallize it. You may melt it and then recrystallize it such that the crystal structure becomes far more pure than you are able to achieve on Earth. And there are some defects that are 3 orders of magnitude less when done in a microgravity environment. And now you have that same, ingot or ball of semiconductor as an example that you can then return to Earth and drop it straight into supply chains. That's really on the commercial side. On the government side, it gets more complicated because we need to both appeal to, for instance, the researchers who are doing the actual research, as well as to the groups who are funding them. And those two motivations can be slightly different. For instance, the groups that are funding them may want to have a good example as an exciting headline, or, move a broader project forward. And so we talk to both of them to say, hey, on the customer side, what are the requirements? And the funding side, what do you need for us to be an attractive platform? And so we really had to map out this whole ecosystem of, who's influencing the process, who the end users are and so forth. And the National Science Foundation I-Corps program that we went through was actually very helpful because I'm from an engineering background. And so this really helped give us a crash course into the right approach to take when understanding these complicated ecosystems, if you will.
Sounds like a lot of diplomacy between the end users and the funders. As an engineer, now an entrepreneur, what's something you had to unlearn?
Sure. So engineer's job is typically to solve problems, while I feel like an entrepreneur's job is to choose which problems to solve. And so what we had to unlearn a little bit is, getting so focused on solving a particular problem because it's fascinating from a technical perspective, and stepping back and saying, hey, what does the customer actually want? And then what's the best way to solve it? Is the engineering approach the best way? Is there another approach that makes sense? And so a good example of this is as we were going out talking to people at the beginning, when we're focused on the human habitat only approach, we would hear these people, a certain subset saying, hey, we don't necessarily need a human space habitat or want a human space habitat. And so it took a bit of humility on our part, a little bit of time to say, actually, hey, this isn't an actual problem. This is an opportunity for us because they have a very real problem that they need to solve. It's not being solved by the International Space Station. We can bake this into our roadmap. It's a win for us. It's a win for them. And so I would say, just making sure that we listen is one of the most important points, and having empathy for the customer.
Speaking of listening, what kind of questions are you asking? What are you trying to learn?
Sure. So there's actually a good book. It's called the Mum Test, which is really about how you get useful information about your startup idea, as an example, from your mother, who's going to tell you that everything you do is great, you're fantastic, you're the best person in the world, you can do absolutely nothing wrong. But that won't necessarily help if you go out and build a product that no one buys. And so really the types of questions you need to ask are not, this is my idea, is it good? Instead, it's more, when was the last time you did something? When was the last time you bought this product or used this service? Why or why not? Why did you not do something? So you're talking about specifics about actions they have taken, and then using that to infer what they would do in, when you present them a product, to really, use their information by proxy, if you will. One alternative that we've also found is not asking them to say, hey, is this idea good? It's to really come in and say, hey, this is our initial approach. What's wrong with it? What won't work? Sort of flipping the question on its head so that they want to give you information that's useful. Where would we run into trouble? So I think those two approaches have really been helpful for us.
Could you also share an example where you walked in with an assumption, a hypothesis, but where the customer made you realize perhaps there's a better approach, there's a different problem that you need to be solving?
Sure. So I'll start with, I've mentioned this already a little bit in terms of the semiconductor side. So we walked in to the meeting and we, had all of this human habitat section here. We said, hey, this is what we can do in some ways, in our mind. And they start talking through and I'm like, what do you want out of a human habitat? And literally this guy said, no humans. We're like, oh no, this is terrible, right? We'd found others who did want a human one, but this one was very definitively no. And this was one of the customer groups we had the assumption of. And, that really just sort of said, hey, we actually need to take this seriously and listen here. Because he said, there's toxic materials in use. There's, high temperatures. There's vibrations from humans that can disrupt this very sensitive process. On the ISS, I have to run this at night. I have to hope that, they don't wake up at the wrong time and move around and cause my experiment to fail. So that was interesting. Now, there's another good example, which is when we came into this, we had a large number of potential customers in mind. And one of them was, 3D printing of organs. We said, hey, a billionaire is going to pay a huge amount for an extra pair of lungs. And, we'd read these articles online saying, hey, this is going to be the next big thing. And so we, hunted around. We found researchers who were doing this, working on biological systems, running experiments on the ISS. And we, called them, we talked to them. And he's like, yeah, there's a big difference in terms of, growing small organoids versus actual full organs. Because there's really these sort of 3 orders of magnitude in terms of scale difference for an organ. Really down to the cell level, what cells are next to each other, all the way up to this giant structure about, how a lung's built and so on. And so just laying down and printing, if you will, or building up the system is a long way away, even though you hear the sort of hype, if you will, saying, hey, this is going to happen. Really soon it's going to be the huge moneymaker. And so that was sort of cause to say, hey, where is the hype and where is the actual real product? Because there is a real product. The organoids that he was talking about for disease modeling, you can make these sort of 3-dimensional cell structures, which are important. The relationship between these types of cells and the structure affects how, a drug acts on them. And there's many different configurations in 3D of these cells. But you can do that in space. You can lay it down. The cells don't just go 2D like they do on Earth. And that actually provides very valuable information for drug companies about whether their drug will work or won't and the effect it has on the body. But now we're getting into the nuance. We've gone from full organs all the way down to, these organoids that we can support. And this changes the type of platform we need to develop and the logistics and the systems that we have to provide.
And just digging a little deeper into the customers and these drug companies, these semiconductor companies who want unmanned systems, how are they controlled? Can you speak to autonomous systems and controlling these experiments, adjusting them when they lie in orbit?
Yeah, that's a great question. So what happens is the customer normally has a process that they're working on, and they put this into what's often a self-contained box. And what we provide is all of the support and infrastructure to it. So these include the power systems, the thermal, the computing, and so forth. And we have robotics on the platform that allows these sort of customer boxes to be plugged in. So sort of the equivalent is on the ISS right now, there's a subset of customers who literally the astronaut's job is to take that box and plug it in and press go. And the rest of it is done autonomously. And really, in some ways, that's a waste of the astronaut's time. It's far better for the astronaut to be working on projects that requires a human in the loop. And so we really see this as a sort of an optimum synergy between human platforms and unmanned platforms. There's an additional expansion beyond that current model, which is we do have robotics on the space platform. And so you can take a large piece of equipment, for instance, a furnace, and install it on our platform. And now we can provide you the extra power that you can't get from, other solutions out there. And, all that's sent up is the feedstock, for instance, in, say, a container, and our robotics grab that and insert it into the customer factory box. The equipment does what it needs to, and then our robot can grab that, now created product and then install it, for instance, in a re-entry capsule for return to Earth. So really, in terms of what the customer gets to control most of the operations on their side, but we can provide, this robotics capability depending upon the type of payload there is and depending on the customer's needs.
To operate these highly complex payloads with power, compute, robotics, it sounds like it takes a village to coordinate. Are you building these in-house? Are you looking at technology partners? What's your strategy and your approach around that?
Sure. So our strategy is really to buy what we can from the market. And then for any of the systems which aren't out there, we develop them internally ourselves. And then we actually take a pretty serious conversation around, if we've had to develop those subsystems, is there a market for those individual subsystems for us to actually sell commercially as well? Now, we are only focused on these platforms, these sort of destinations in low Earth orbit, if you will. And so, key partners are, the launch companies to get products up there. They're the re-entry partners to, move products back to Earth, and even potentially, the orbital transfer vehicle companies. If there's one-way, payloads that don't need to return to Earth, then they can pick them up and deliver them to our platform. And so it's really a village. We really rely upon these other partners for these logistics capabilities. But we aid their business cases by expanding the number of markets they can serve and, providing different capabilities than any of those individual partners could do by themselves.
The supply chain aspect. Where do you see the market has matured and you're able to easily access parts, components, the technical know-how? And where do you still see some challenges, some gaps in really scaling these for thousands and millions of use cases?
Sure. So that's actually a really good question, because right now the industry is, for the most part, at the point of, batch production. Now, you are getting true mass production when it comes to, for instance, Starlink or some of these constellations, for instance. And so you can piggyback off on components that are, destined for them. Components, down to the level of reaction wheels, for instance, or regular bus components are ones that you can buy. Solar arrays themselves are in the sort of interesting transition zone where the cost of the cells are coming down, the cost of the deployable panels are coming down, but not quite as fast, and hasn't quite reached the point of actually being a proper off-the-shelf product. It's getting close. There's a few other subsystems in there that really require more work, particularly around the robotics. So there's been some interesting advancements around that we can take advantage of, but there hasn't been the level of demand for robots and robotic arms, for instance, in space, as there have been for solar arrays, as a good example. One area where everything is maturing is not so much a product, but the capability of doing rendezvous and proximity operations. So this is when one spacecraft, comes in close and docks with another, which of course is critical for our, platforms. Otherwise, there's no way for customers to get to us. And that's one that's being actively worked on. And so it's one way that we can actually help in that regard, because our platforms are well prepared. They're designed to be docked with. We have this robotics capability to aid in docking and berthing. So it's completely different from one spacecraft coming in and trying to dock with an unprepared spacecraft. That may be a, defunct satellite that's now spinning in a random orientation. That requires a huge additional level of complexity, but it's what needed if some of these companies are wanting to do orbital debris removal, for instance. So we can aid in the expansion of that capability by providing this nice prepared target that allows them to test things out in a more benign environment.
ISS, the International Space Station, retires in 5-6 years. Axiom, Orbital, Reef, Sierra are vying to replace it. Where does Astracene fit in? And what's your moat that other contemporaries cannot copy?
Sure. We're able to provide the unmanned platform before the ISS is decommissioned. And we're able to do it a lot more quickly simply because, it's an unmanned system. We're able to do it at much lower capital costs as well. And so we really feel into the niche where, consumers of the ISS will be needing a solution even before it's decommissioned, because the ISS gets booked up, years in advance. And that allows us to be there and say, hey, we're compatible with ISS payloads. Come fly on us if you don't necessarily need human involvement in the loop. And so for the payloads that don't, this becomes an attractive proposition. In terms of the moat, for instance, well, on the habitat side, for sure, as I've been talking about this patent pending approach to the actual habitat hull itself, we have the centrifuge technology that we've been developing that's applicable not just to humans, but even to smaller scale centrifuges, such as for simulating the lunar environment for a long duration, for instance, or for performing 1G control. So this is sort of very different than what's being developed by other companies right now. There's a couple of other subsystems that we're working on where we do have an advantage, but we're keeping them quiet for the moment while we're developing them out.
You have the Earthshine Mini, the Earthshine Robotic, and the Earthshine. And then you have plenty of complex electronics inside these structures. How do you power them?
Sure. So we power it through solar. And solar is really going through sort of a renaissance right now for the space industry. The prices for solar cells are coming down. The cost of launching mass to space is also coming down. And so together, this provides an opportunity to really expand the use of solar. There's some really exciting developments within the field of solar cells itself in terms of what's called annealing. So that is when you have radiation present, the radiation comes in, they knock out the location of atoms in the atomic structure, and that actually reduces the performance. But if you heat up these solar cells, it can actually cause these atoms to pop back into place. And so the performance can actually increase if you operate them at high temperature for a while, annealing them as it is. And so there's a lot of active research around that. And if that is successful, then it will sidestep a lot of the problems you currently experience in terms of degradation of cells over time due to radiation. So it's really it's been promised for quite a while, but the results are finally coming through. The studies have been completed. It's going from just being promising to actually being something that's a near-term possibility.
And one of the reasons why the ISS, why it's retiring, is its aging infrastructure. Could you speak to the longevity of your space habitats, of your platforms? How long are these systems supposed to last?
Sure. So for the uncrewed ones, the minimum is about 5 years. And this can potentially operate far longer than that, but that's the time that we need to have for it to, make sense for a variety of reasons. The human habitat ones do need to last a lot longer. And so the ability to embark upon repairs or upgrades is really something that we had to incorporate into the system. We can provide sufficient shielding for micrometeoroid debris and other such factors, but in the unlikely event that something gets through a bit further, we had to have a plan in place to repair it. And so I would say that the ISS, there's a lot of challenges in terms of repairing the ISS. You have all of these equipment racks right up against the walls. Tracking down leaks can be very hard. And there's just a lot of lessons that have been learned from the process in terms of how to sidestep that and just make it easier for everyone in terms of repairability and maintenance, as well as designing it to be more leak resistant in the first place.
Right. There are a series of founders who are solving for power using small modular reactors, SMRs. You are using solar as your main source. On Twitter, on X, Elon Musk wrote a very long tweet about solar is the definitive quintessential source. How do you reconcile this tug of war between alternative power sources and solar?
Yeah, it really depends upon the use case in a way. So you have the case of like nuclear propulsion, for instance, in which case you're really using your nuclear reactor to provide the energy required for propulsion. And that has very interesting applications in terms of getting to Mars quickly, for instance, just getting to the moon quickly as an example, going places that you need a lot of delta V very quickly. It's also, nuclear is very relevant in places where solar is not as applicable. If you're going out to Mars, for instance, the solar array is probably about half as effective. If you go further out, it gets worse and worse. And so you get a lot of benefits from going to that place. The challenge, of course, is the regulations around nuclear power make it very difficult not just to build and launch, but just to do R&D on it in the first place. While, since everyone's been using solar arrays for 50 years, there's a lot more confidence in the abilities. And if, for instance, I'm working on, I have the space platform, the solar arrays are not my core business in this case. So I don't necessarily want to invest a huge amount of R&D into that area if I don't have to. There are systems I absolutely have to do so, but that's not necessarily one of them. I can go to other companies with that expertise already and, purchase them for less than it would cost me to develop them in-house. So solar really has that advantage in that it's more of an off-the-shelf product, but there are definitely advantages to nuclear in these certain use cases, and it would quite possibly be competitive with solar if we had had 50 years of development for use in space alongside solar.
What remains the biggest technical or engineering challenge that perhaps is unsolvable because we're too early, we're too nascent in this business cycle?
So I would really say it's in some ways closer on the human side, and the key challenge is almost less technical and more ensuring the market is there for humans in space. And so that's one thing we're actively working towards, ensuring that the manufacturing industry comes along and is ready to support people in space. I would say that while there are a lot of technical difficulties around keeping people healthy and fed and safe, these are all solvable. People have been working on this for many years. We've had people in space persistently for many years, thanks to the ISS. And so there's nothing that's insurmountable. It's making sure that the foundations are in place for them to not just be 4 people or 10 people, but actually this exponential growth.
So finally, Lee, semiconductor fabrications, big pharma, and NASA program managers, how do they contact you?
Sure. So one of the best ways that we've found is actually going to these very niche conferences that are focused specifically on these different groups, particularly on the manufacturing side, for instance. If there's 24 people at the conference, but there are 24 people who are all focused on making a product in space, that's fantastic, right? We can go there, we can get ourselves known, we can know what their requirements are. So similar on the NASA side. And then, of course, a lot of it's networking as well. We meet one group of people and they're working on one product. They say, hey, we know others in the industry. What you're working on would be really beneficial to them too. Let me put you in touch. And so it's very much this sort of network effect that starts growing. And in some ways, the longer you're around in the space industry, the more useful contacts you get.
Perfect. This has been Space Terminal. I'm Zuni from Imagining Forward. New episodes are out every week. You can find Lee and Astracene in the show notes. You can also look up Astracene on our intelligence tool at imaginingforward.space. Thank you, Lee. Thanks for joining.
Thanks very much.